So again, the equation of motion and then the natural frequencies. So for this case, again, we have this is a rigid bar. And usually we don't consider it has a mass, okay? Making the thing simple. So again, if this is rigid, then this is, it seems we're picking up the theta as the degree of freedom. So, sorry, this has mass. Okay, the mass is equal to m. So for this case, we need to determine what is the equation of motion something in this kind of template. So that is first things. So from here we can take is this, because this is a rigid. And once is displaced and rigid as a straight line after deformations will remain as the straight line. Okay, so this is being do a little tilting by angle theta. And again, in linear vibrations, we assume the theta is small. Okay, so that means here we have a spring here, and this spring moved to here, so that is the displacement of the spring. And also there's a displacement of the spring here. So we need to determine the two sides. And again, here we assume the theta is small, so that means very, very small. So, so basically this is, in reality, if you want to calculate this one, this should be taking the tangent or sine, whatever. But for small angle, basically it's barely tangent theta is equal to theta, or sine theta is almost equal to theta for small something. So here we simply take out this portion simply is taking the distance here multiplied with theta, so that is a theta. Okay, the distance here simply is L and multiply with theta, that's L theta. That is similar to you if you have the arc here. Okay, so that is the same concept, r theta, this arc equal to r theta. Similar idea like this. So under this one, we figure out the displacement, so then we're going to impose the force, okay? And this one going down, the spring of this one stretch. So at that point, the spring will provide the force up. So that is K1 times A theta. Okay, and this spring at here has been compressed, so this end the spring we're going to apply upward loading due to this spring, and that is equal to K2 times its deformation. Deformation is L theta. Okay. Furthermore, we have a spiral spring here. Spiral spring is such that it's always to oppose its deformation. So right now, the deformation is in this way, so the spiral spring going to provide a torque in that way. So that is K, let me call it KT theta. So let me say this is KT, okay? So again, I want to emphasize this is a force, and this is a force. For spiral spring, again, due to its unit, this is a torque. So remember, keep those kind of quantities in mind when we do the formulation. You won't confuse, okay? And okay, because on the other side, this beam has mass, so that will be equivalent to, because this is a pivot here, okay? So there's a pivot. So that means this is the mass of the rigid bar, and because it has a degree of freedom assigned to here, so that means it has the moment of inertia, let me call the IO. I is the moment of inertia with respect to the pivot O here, let me call the pivot O here, okay? And times theta double dot, so everything must be equivalent, so that means the moment about the O would be equal to, using Newton's law, IO theta double dot. And again, taking the sign conventions, I like to get the sign convention aligned with the degree of freedom. So let me take this as positive here. Okay, so therefore from here, IO theta double dot on that side, we have KT theta minus K1 A theta times, this is a force. Force multiplied with distance gives us a torque or moment. And again, this one, K2 L theta times L. Okay? So right now we rewrite the last equation here. So IO theta double dot plus theta KT plus K1 A square plus K2 L square theta equal to 0. So this is our equation of motions here. And if you, one more step, yes.
Should we include gravity in this?
Gravity?
Yeah.
Here, yeah, although here we have a gravity influence, again, when we define our degree of freedom theta, it's found its own equilibrium configurations.
Okay.
So equilibrium configuration will be a little bit not completely horizontal, maybe a little bit down below due to the gravity.
Like always assume?
Yeah, always. We always assume from the equilibrium. Okay. So from here, if you want to furthermore criticize and not criticize to more in detail, IO is the moment of inertia of the stream with respect to the one end. And again, if you remember the dynamics, and that will be mL squared divided by 3. Okay, I know this number because before I came here, I reviewed my lecture notes. I simply memorized. So keep those things in mind. So in this way, you can have equivalent description theta double dot plus omega n theta equal to 0. So here omega n should be equal to, put everything here, kt plus k1 a square, k2b l square, and divided by io and l square divided by 3. Okay.